Hello and welcome to Q for Problems, Episode 3, Part 2. So in Part 1 we were looking at Problem 3 from the Project Euler problem set, which wanted us to find the largest prime factor of the number shown. And we used the trial division algorithm to find the answer. So we're going to look at the Pollard's row algorithm, which can also be used to do prime factorization. So if I jump over here into my developer, I've got the algorithm already predefined here. So you can find this kind of definition on things like Wikipedia. So text-free arguments: x is an integer value chosen by the user, f is a function used to generate a pseudo-random sequence, and n is the value we're trying to factorize. So it starts by setting y equal to x, so these are starting values, so they'll start at the same value, and g equal to 1. So yg is equal to 1, we'll continuously do these three steps, and once it becomes not equal to 1, we will return g. So the steps are to apply the function to x and reassign to x, apply the function twice to y and reassign to y, and then to do the greatest common divisor between the absolute value of x minus y and n. So I will discuss the greatest common divisor in a minute. So the idea here is that these generate pseudo-random sequences, however the sequences are expected to repeat, in which case, because y is having the f applied twice, it's actually going to change twice as fast, and it will go round in its sequence twice as fast as x, so eventually it will catch up to x. So that is the idea of the algorithm. So this is the base algorithm, Pollard row 0. The actual algorithm itself then takes the actual predefined f of x. So this is the commonly used form of the f of x. C is just another, like x, the original x, it's like an integer chosen by the user. It's usually 1, however it can be anything. So this is the common formula for generating this pseudo-random sequence. So essentially this is our f of x, and we're passing that to the projection of Pollard's row with the x and n value already given. So all you need to do then to use this formula is to choose your x, choose your c, and pass it the value of n, which is what you're trying to factorize. So if I jump over here to Scratchpad, so this is the number we were trying to factorize, n, and then if I run this function Pollard's row, you can see that actually gives me a value of 71. So the 0 is the x value and 2 is the c value. How did I know about these? Well, with trial and error I was able to find that these were the appropriate numbers to factorize this. However, we will discuss how you can choose this, for a general case, and how the function can actually do it for you. So another thing there I did say I would go back to is the greatest common divisor. So the greatest common divisor, which you might remember from maths, is defined as a if one of the essentially if b is 0, and otherwise it's the greatest common divisor then of b with a modulus b. So jumping back into our Scratchpad here, so if I say start with a equals to 15 and b equals to 10, so this was just like an example starting point. So we want to do the greatest common divisor between 15 and 10, which we know is 5. So that's what we should be expecting. So going by the definition, it should be group GCD of 15 with 10. That should then, what we need to do is check, is the second value 0? If not, okay, let's do the next step, which is to do the greatest common divisor of b, so our original b, which is 10, with a mod b, which is 15 modulus of 10, so that would be 5. Again, b is not 0, so we need to go on and do the greatest common divisor again. So this will be our b value, and then it is the a modulus b, which is 10 modulus 5, which gives 0, and in this case our b is 0, which means that we just return a, which is 5. So this is the functionality we're trying to recreate. So first of all, we would need to be able to generate, in the case that this is not 0, we would need to generate this next sequence of terms, i.e. starting with 15 and 10, we need to generate 10 and 5. Well, we can do that pretty easily. So we'll just say n for next, and it's going to be b, which is going to give us our 10, join with a mod b. So you can see there it gives us our 10 and 5. And if we were to say assign A equals to n0 and B equals to B assigned to n1. So this would actually be us now ready for the next iteration. So if I was to run this again, you can see now it gives me 5 and 0. If I assign this again and then I was to check that this is 0, I would just return 5 in that case. So how can we do this then essentially iteratively? We can actually just use the while form of the over accumulator to do this. So what we need is first of all the function that's going to be applied. So it's going to be essentially just what we had here, but in its functional form, i.e. taking x as an argument. So the mod dot here is the binary application of mod to, so this expects x to be two values, which will be, say, starting it will be 15 and 10, and 15 will become its left argument and 10 will become its right argument. So it applies to that, and then last will be the 10, for example, i.e. the b each time. So if I start that and do that with 15 and 10 and run that, you can see it gives me 10 and 5, and then if I was to take 10 and 5, it gives me 5 and 0. So that's the way exactly we want it to go. So we need now to add our predicate, which is going to say when we want this to stop the iteration, and that is when the last item, i.e. b, is less than 0. So this will keep going while the last item is greater than 0 until it's not equal to 0 anymore. So all that's left then is to use the over. So I'm going to actually use this scan just so we can see the intermediate steps. So you can see here it started 15 down, then went to this, and then went to this, and then stopped. So if I actually use the over, you can see it will give me 5 and 0. So I just want to select the first from this, and that is our greatest common divisor function. So you can see it here in actual function form. I'd rather people just pass two values, so x and y, and it just joins them and then does exactly what we had then. Interestingly too, if you want to say do the greatest common divisor of multiple numbers, you can just use over as well. So say I had it's a good example, say like 12, 18, 42 and 60. So that will be the greatest number that divides into all these numbers. So you run this and you get 6. So what it does is it will apply the greatest common divisor to these two first, get the value, which will be 6, and it will do 6 and 42, which is still 6, and then it will do 6 and 60, which is going to still be 6. Essentially it just iterates over the top of that. Okay, so that's the greatest common divisor. We can now return to our Pollard's row algorithm. So as you've seen there before, if I go back here to the start and just run these two lines again, you can see this actually only gives me one number. This is only one factor. So we have to constantly apply this to get the other factors. However, what we can do first is, this is one factor and factors come in pairs, which means if we divide this number by the factor, we can actually get another factor, which then itself can be factorized. So the one we will get might not necessarily be prime. So how can we actually do that? We can just do p join with n div p, and you can see now we have factor of 71 plus this number divided by 71, which gives us this. So if I was to multiply these together, it would reproduce the original number. So I want to assign that back into p. Sorry, I have to do p equals this. Okay, so now p is our two factors. So the next step then is to essentially repeat what we just did. So I'll say p1 is equal to, and then we'll do Pollard's row on each of p. So we're doing it on each of these two values. So if I run this, so you can see now this was able to be reduced to this factor. However, 71 is already prime, so it can't be reduced any further. Pollard's row just returns the number if it can't be reduced any further. So essentially what we have to do is, we don't want to keep doing it on these prime numbers because it still has to run the algorithm and check multiple times before it can return this. So we actually want to filter out these numbers that we already know are that it's already seen before, essentially, that can't be factorized any further. So to essentially do that, we can say our p2, is equal to P1 on I where it's equal to P not equal to P1. So what's going on here? So this is checking our original P. Oh, sorry, get rid of that. Our original P, which is what we had there just before we started, 71 and this number, and checks is it now equal to when we apply the thing again. So the 71 is going to be equal, which means that it's going to return a false value, and then this number has been able to be factorized, so it changed, so it gives us a true value. So we store that in B here, we're using that. And then we want to say where, i.e. the ones that were able to change, those are the ones that we're interested in, because we might need to keep reducing them further. And so we just index into P1 to get that number and assign that to P2. So what's left to do then? So we had our P1, which had these two numbers. So we need to join on, like we just did here on line 3. We need to join on the ones that have been able to be factorized. So if I just run just this part, you can see this actually gives me this number divided by this, which is this. So this is another factor. However, we do need our original two factors as well that we did have. So 71839 plus this new one. So if I run this, you can see now we've got another factor, and we essentially then need to repeat again and repeat again until it essentially doesn't change at all. So this might be a bit clearer then if I put it into a functional form. So say f is equal to p join x of I div by p on I where x to p Pollard's row 0, 2, and then each of x. So this is essentially what we had here. This is the Pollard's row each of x part is p, and then checking that they're not equal. We only want to actually do this divide part on the ones that are applicable, and then join on what we had originally from this. Now, of course, this is doing on each of these Pollard's row. We would need this to be in a list form essentially. So when we start, we can actually start with n as just a single value. We need to start with a list of a single value. So we can just use one tech to quickly create that list. So now if I do f on n, you can see it gives me this. Let me just clear this as well to make this a bit easier. So if I do f on f of n, you can see now I've got 3 terms. If I do f on f of n, you can see now I have 4 terms. And then if I do f on f on f on f of n, you can see that it did not change. That is the point at which we would stop. So we can actually do this using the over accumulator. It has a converge functionality in it, i.e. whenever it sees the same value twice produced in a row, it will actually stop. So all we need to do is do f over and then our n, and you can see it will give us the same value. So it will stop iteration once it sees this twice. So yeah, essentially we want now to make sure that these values for Pollard's row are configurable. We need to add some special handling as well for the case that numbers below 2 are handled. So if I just jump over here now to Pollard's row 1, row fact 1, you can see here now we had this before, just if it's less than 2, we just return it because it can't handle it. And then we also need to pass in this x and c value, which essentially goes right into Pollard's row, so it's more configurable. But yeah, everything else is as we had it before. Yeah, so that is the first solution of the Pollard's row. So if I was now to run max row fact 2, this, you can see it does give me the correct answer. Unfortunately, this algorithm does perform badly when there's prime number inputs, and of course we do need to decide these two numbers. So these are the two issues that we have. So first, filtering out the primes, and so if we start from say the case where it was 71 and what was that other number, if I grab it here, so we say n equals to 71 and 8th, whatever number that is, just do capital in here. We can use the is prime that we this comes from a blog post as well, the same blog post I mentioned in part 1 about generating the prime numbers, so you can go take a look at that blog post. It'll be in the description. However, we check if these numbers are prime. If they are, we don't want to apply this again, so we essentially need to filter those out. So this essentially means making a small change to the function. So this is row fact 2 now we're going to be looking at. Essentially a lot of it's the same. The major difference is this part now where we do the prime filtering. So we say, is it prime? And we only want to consider the ones that are not is prime essentially. And then we will join the prime ones back on at the end here. So that is just a small modification, so that we're not continuously checking prime numbers, because yeah, the algorithm can perform bad for them. There's also a problem that there are some numbers, if you do not choose x and c appropriately, you can't actually factorize the numbers. So a good example here is 100 with 0 and 2. So if I run that, you can see it's 5, 5, 4. However, this should be 2 and 2. It wasn't able to factorize the number 4. So we can actually make another modification to the algorithm. So essentially what I do here is check the output of row fact 2, which you just seen, and if there are any numbers which are not prime. So essentially this checks, is all the values prime now, i.e. is it all prime factors? If it is, we just return those factors because they can't be factorized any further. However, if there's any that still aren't prime, i.e. the 4 in this one, that will actually just then be passed to pfact2, which we've seen in the previous video, part 1, and that just refactorizes those, because this is a good algorithm for smaller numbers anyway. So it's actually okay to do it like this. Finally too is, of course, instead of doing this, where we're essentially falling back to another algorithm if we can't use this algorithm, there is another option. We can actually do a random version of this. So what it will actually do, so this is row fact 4. So you'll see it looks basically the same as row fact 2. However, what's different is this Pollard row here, and you'll see that this isn't actually accepting a c and an x argument like we have in the other ones. So if we look at Pollard row 1, that is because it's actually calling this Pollard row with a random number. So this rand n essentially generates a random number, a single random number between 2 and n. So that is what this function does, and that is our x value, and then our c value as well. As you can see, it's also a random number between 1 and n. So I won't get into how the rand works. It's just using the KDB's random function. It's quite simple. Maybe discuss it in a future video, but essentially it's just generating a random number. However, this is, and if you get the code, on Git, you can have a look at this function itself. But yeah, this will actually generate those x and c values randomly and continuously do it like that. The only thing is there are still numbers. This will actually keep going until it finds a solution, and there are numbers that can't be completely factorized with any choice of x and c, in which case you actually get an infinite loop, which isn't good. So I'm not a big fan of this version, row fact 4 of the algorithm. However, row fact 3 is, it's complete. It will be able to completely factorize everything, and it doesn't matter about your x and c. That will only matter for performance, but you will still eventually get the right answer. So looking at performance, if we look at the number in question and compare all the row fact 1 to 4 with the pfact 1 and 2 that we've seen in part 1, we're going to run this 100 times. So it might take a few seconds here. However, this number does, as we did see, has smaller factors. I think the largest one, the max factor, was 6,800 something. You can see here that the actual best one is row fact 1 in terms of time. and pfact1 in terms of memory, but rowfact1 isn't too bad different in terms of the memory. However, if we look at a number with a larger factor, so what I mean by that is if I was to run pfact2 on this number and run that, so you can see this has actually so the biggest factor from the number in question was 6,000 of them, but this has a number in the millions. So if we actually run that, the most performant solution was pfact2. You can see pfact1 was actually quite unperformant for this. However, the best of the rowfacts was actually rowfact4, where we would do the random assignment of the numbers, and that is probably because the choice of 0 and 2 were quite bad choices for this particular number. So this did perform quite well using its own choices. However, because it's random, you might run this again and it might not be as performant. And this is a large prime number, so this number is already prime. So if I was to run pfact of that, pfact2 of that, you can see it just returns itself because it's already prime and it can't be factorized anymore. On that large prime number, you can actually see that rowfact1 is actually quite underperforming. Like it's like I said, it was quite bad with dealing with primes, this algorithm, because we're not actually doing any filtering to get rid of the primes. We're just constantly checking, and that's going to perform quite badly. However, the best solution for the large prime number, it actually was rowfact2. This could have been better. It just depends on the random assignment of the x and c values. But yeah, that's everything for prime factorization and problem 3 of the Project Euler problem set. Please post your solutions below and check out the Git repo and the SharePoint if you want more detail into these explanations of these functions. And yeah, thanks for watching.